So thank you again for having me. And also, thank you for being here and listening in. So today, let me just say again, I'm going to continue on with what I was doing yesterday. I have just a little bit of stuff left from the classical part of the conversation yesterday, so I'll do that. And then we'll move on to the quantum stuff. I just want to say that for those of you who attended Carl's lecture today morning, this is going to be essentially just a repetition. A lot of the essential ideas he's already presented, so I apologize for that as well. Okay, so yesterday, let me just recap very quickly where we were. So what I had pointed out was that the variance of the estimator, and today I'll switch to theta just to remain, okay, I'll keep it at phi, so that variance of phi is larger than or equal to 1 over this quantity g. I made a mistake, I wrote it as g and then I corrected it, but I want to super emphasize that it should be in the denominator. So this is one of the things I wanted to do. This quantity is basically the expectation value of, so I wrote it as several things, including integral dx p of x comma phi times log p of x comma phi by del phi. Okay, and I was basically saying yesterday that we'll motivate this in several different ways so that you gain intuition, and I can share the intuition that I have with you. So one way was just this matrix inequality business yesterday. So you can think of it essentially coming from some sort of Schwarz inequality type derivation. Almost all of this is some cousin of Schwarz inequality done again. Here is the other, let me leave this here. Here is the other way of thinking about it that I just started yesterday, which is I said, consider, so this is, so this quantity is called the Fisher information, right? And so what I promised you was that I'll try and motivate Fisher information a couple of different ways. So this is Fisher information via Kullback-Leibler divergences, right? And so, so I asked you to consider basically the Kullback-Leibler divergence between two probability distributions P and Q. And I wrote them as sum over I, Pi log Pi over Qi, right? Both these Pi's are the same, right? And I had tried to kind of point out to you that this is this notion of average relative surprise. So this is surprise, and this is the averaging process, right? So if I have two probability distributions, I can ask the question, how surprised am I if I was expecting one probability distribution, Pi, but you kept giving me samples from the other probability distribution, Qi, right? You can imagine why this is an important thing in the discussion of probability theory, because in the discussion of probability theory, this is how you would begin to define basically how probability distributions vary as you vary some quantity underneath. In this case, the parameter, the unknown parameter that we wish to study. But it has kind of deep significance in classical as well as quantum information theory, in fact. Okay. And so let me make several comments about KL divergences. Right. So this has several names. So sorry, let me just write down. And I apologize, I should have looked up. I'm not sure about the spelling here. It's also called the, we would call it classical because we have something else, which is quantum. Right? And so what I want to do is just assert some comments about this relative entropy without, with little proof on some of these. So point number one is basically, it also has this notation S. So sometimes it's called KL, sometimes it's called S of PQ, sometimes it's called SKL of PQ. All these things mean the same thing. So S of PQ is a positive semi-definite quantity. This you can prove. You have to work on this a little bit, but you can prove this. Right? Again, all of the references that I provided have this proof. Nielsen and Chuang, for those of you who are adjacent to quantum computing, has a proof which also includes the quantum cousin of this. Also true in the quantum case. So you can look that up. You can just ask me offline. So second thing I want to make, this is important for something that I'm going to say to you about thinking of minimas of this function. So it is equal to 0 if and only if P is equal to Q. This you can prove. Strong statement. Okay, good, yeah, thanks for that. The second thing I want to make is that S of P Q is actually not symmetric. Right, and remember here, you can see it functionally in the formula. P appears twice, Q appears once. So P seems to have a slightly different role than Q. If you exchange them, they're not the same object. Here I want to make two comments. One is it means that it loses the property of distance. Right, remember that distances, when you define distances between any 2 points in a space, right, they have to be positive semi-definite, which this thing is. They have to be symmetric, and they have to obey triangle inequality. This thing doesn't do the last two. Right, so the symmetry is already gone, so you can just forget about anything else. And that's the reason why it's actually called divergence. That's the reason there. Right? In fact, it can blow up to infinity. And that's another reason why it's also called a divergence, but I'll point that out in a second now. The second thing that I want to make is an extra comment, which is that if you want to symmetrize it, there is a whole method to do this, and it goes by the name of Wigner Yanis, and I invite you to look that up. So there is some construction here attached to that. The third comment that I want to make, perhaps I'll make it over here. Okay. The third comment I want to make about this quantity, SPQ can go to infinity if basically there exists Qi equals 0 for which Pi is non-zero, right? So there is a nested kernel property here. So if all the zeros of the probability distribution of Q don't line up already with P, then P over Q can blow up, right? What does this mean physically? I expected non-zero value of outcomes in the event I. I got 0. I'm heavily surprised by this, right? So it makes sense that it would blow up or do something strange, which would signal to us that you have to pay attention. There's something happening here, right? Mathematically, this is what happens. Nothing. Okay. And the fourth, and the thing that is the most interesting to us, and essentially the reason I've introduced this, is I can now ask the question, what is S of P? Now let me actually put all the labels in. A variable X, given that I have a parameter phi, I want to compare it against a probability distribution. Let me call it Q of X given phi plus d phi. I want to ask this question, right? So let me explain mathematically what this is, or physically what this is. What is P of X comma phi? What is this experimentally? Sorry? It's what about the measurement? It's the probability that you get the outcome, right? So I have on the x-axis something I'm measuring, which I call X, right? Could be just the bin that I'm collecting my events into. So it could be up spin, down spin, whatever, right? 0, 1, 2. And I have a probability distribution, basically, right? I have a probability distribution P of X given that my parameter was phi. Remember yesterday I already kind of signaled to you that P of given that the parameter is phi is, where is it coming from? It's actually the trace of some operator Ex on some density matrix rho phi. I will introduce both these objects today. Whatever I want to measure. I could, phi is the phase acquisition. So yeah. So this is the acquired phase from the quantum system. So it's like e to the minus I phi g, rho naught e to the I phi g, this quantity. Yeah. So so what am I saying here? I'm saying I have a quantum state, initial state rho naught. I take it, I evolve it according to some phase phi, right? And some Hamiltonian, some generator G. And then I want to look, let's say, where it is on the real line. I want to look what is the probability, the frequency of the spins being up. These are all examples of the variable X, right? One continuous, one discrete. Yeah. And so you can ask this question and you get some histogram like this at the end of a million measurements. You'll get some histogram, which I'm approximating with the probability distribution I'm doing. Now, what I'm asking is, if I change the underlying parameter from phi to phi plus d phi, suppose I had this in my hand, right? And I put basically the glass plate whose transmission coefficient we were discussing yesterday, I change it a little bit by shaving it or cleaning it or doing something to it, right? That would strip away a little bit of material. Then I've gone from phi to phi plus d phi or phi minus d phi, whatever. And now I'm asking, how does this probability distribution change? This is the question I want. Why? Because if it changes very heavily, let me show you a dramatic example. Suppose it changes like this. That's very easy to detect, right? So don't look near the origin because the kind of histogram is the same. You know, it's similar, so the numbers are the same. But if you look over here, you expect very high numbers, but for one and very low numbers for the other. Which means if you just look here, if you look here, you look all over the place, you get the answer that you want. right? Yeah. Absolutely. And I'm just talking, so before we set up this entire machinery, I have to basically first tell you a series of different things have to be declared to us. One is, what does phi belong in? Right? Two is, what is my Hamiltonian generator? Three is, what is my density matrix, so on and so forth. All these are all things that fix the instruments, they fix the way that I'm acquiring the phase. All this has to be fixed already by hand, right? And the reason why this is fixing the instrument and so on and so forth is this is the difference between using a ruler and a screw gauge and a vernier caliper in measuring length. Yes. 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 So two things I want to say. One is the machinery that is in front of you right now is about local estimation. So it's actually not even about any number inside this. It's about the fact that you know that you were here a second ago, and you're just asking how sensitive am I to local changes, right? So this is, and so the entire story can change the moment you start changing, right? And in fact, it usually does. So let me give you a very, very physical example that I can think of. If you think of a detector that you build that you want to detect light, right? So you have a light dependent resistor, for instance, right? These things have saturations. And if you hit the saturation, then it doesn't matter what you're trying to measure, like how much light is coming through after that. No differential increments of the light that is incident on the detector would actually be able to excite the detector, right? A typical kind of avalanche photodiode, inside of its dead time is unable to respond, right? So there are any number of kind of reasons that you can think of why your detector will not respond. And the first example that I gave you is actually an example where the parameter itself is changing, and the detector is unable to respond because it's outside of the detector's response range, right? And all this is the messy business of a real detector. There are ways of modeling all of this. I can talk to you about it offline. We can model lossy detectors, saturated detectors, so on and so forth. And then there is also this other example that detectors usually have like lags in the way that they respond to signals. And this also can be modeled, but you have to work a little bit harder. This is idealized. This is throwing all this messy business, which actually makes the measurement even more imprecise, usually, throwing it all away and simply asking the question, if I had the best detectors and they had the best response times and you didn't have a problem where you parked the parameter, you didn't have a problem changing, tracking changes, what's the best you could do, right? So I'm throwing caution to the wind and I want to make the best physics sensor that physics will allow. And that is good for local tracking. Again, if you change it to global tracking, so if you say, look, I want to know the number between phi min and phi max, anything I want to know, that's a completely different problem. And you have to work a little bit differently to do that. And I believe that Saikat tomorrow will handle this question. I will touch upon it, but we exchanged a couple of comments where I understand that he's going to talk a little bit about it as well. Okay, so this question is simply the question of local tracking, right? So this is so if you look in literature, you will see this notion of local versus global metrology, right? And actually, this is what they're referring to. Global means I want to track the parameter anywhere, and usually you have to go through mean square estimators and things of that sort. You just have the kind of mean square estimators, and you have to work to kind of do something with that. Whereas local estimators, you can actually try and design the machine directly, right? And so this is, well, okay. So let me go back and make the point I was trying to make. So I want to know how this probability distribution drifts. And the other dramatic example that I want to note is something that's like that, right? Which is right on top of the previous distribution. This is very bad. If my parameter changes by a value d phi, and my probability distribution, my histogram underneath doesn't change at all, there isn't any information sitting in the histograms for me to work out what my parameter drift could have been, right? So do you agree that for the case of local tracking, like local parameter estimation, for the case of detecting d-phi, basically, that this quantity, the quantum, the classical relative entropy between the two parameterized probability distributions is a good place to start? It tells you something, right? And now I show you within 1 second that it's actually just the Fisher information that pops out of this as well, right? And this is, as Carl was saying today, the reason why this thing is called an information. Okay, so how do you do this? What I do is I write q of x comma phi plus d phi as p of x comma phi plus dp of x comma d phi. Right? So this is a tautological statement. So this statement, p is given to you, q is given to you, so it defines this quantity dp. Right? Do we all agree that if you integrate q, it's a probability distribution, should go to 1, or sum it, right? The sum of this should be 1, which means this should sum to 0. Right? So essentially all I'm saying here, what is dp? dp is basically, I erased the diagram. If I have one probability distribution like this and another probability distribution like this, I'm essentially just taking this difference at each point, right? And I'm writing it as dp, right? Okay. Phi is the parameter that doesn't vary in, but yeah, so the integration is over x. So x basically represents the current that you're measuring in your device, so on and so forth. Phi represents the beam splitter, transmission coefficient. It represents some voltage that you've applied to some physical system, so on. It's the parameter that you're trying to go after. So you're asking the question, I have some current and it's doing something, and now I change the voltage by a tiny bit. How magnificently does my current shift? Right? Because if it shifts by a huge amount for small changes, then this is fantastic, right? Agreed? Right? There is a way to make a precision length sensor, What is it? It's to make me stand here, right on the table, at the edge of the table, right? So small variation, I fall and you hear it. You hear me crying, right? So what you want to do is you want to be at the edge of something where you have a very severe change in the response of the function when you change the variable by a small amount, right? Hold on to this thought. I'll come back to it at the very end of this lecture on basically how to use critical phenomenon, phase transitions, to actually build sensors, right? You can actually build sensors because right at the phase transition between, water and ice or whatever, the system is very susceptible, it's highly susceptible. Okay. Point for a different time, but let me just move on very quickly. So then I just plug this in here and I Taylor expand. So what I do is I do S, I'm just doing this in shorthand, P plus dP is sum over Pi log Pi by Pi plus dPi, but this is sum over Pi log 1 over 1 plus dPi over Pi, which is basically sum over Pi log 1 plus dPi over Pi to the minus 1, right? And this quantity is approximately sum over Pi, and then I have to do this log expansion, and the log expansion is x minus x plus x squared over 2. So the leading term is x, which is dPi over Pi, and the next order term is dPi squared divided by Pi squared. Can you still see this? Yeah, let me write it on the wall again. Right, so the Kullback-Leibler divergence between P and P plus dP is approximately sum over Pi, and then I have to expand out this log term, and it produces dpi over pi, and then there is a 1 over 2, which I forgot here, dpi squared divided by pi squared, right? And then there is order dpi cubed stuff, which I can just ignore. Yeah? This quantity, when you sum over, this cancels and that cancels to 0. You see that? And the leading order term is sum over I, 1 over pi times dpi squared with a half. And that's just the Fisher information. Yeah, so the meaning of this analysis, I just want to say very quickly, the meaning of this analysis is the following. It's simply saying to you that if you want to think of a measurement and what happens to a measurement, you collect a histogram's worth of data. You don't collect, right? You typically collect a histogram's worth of data, a probability distribution function if you abstract it out. And that histogram, if you now ask what makes the most sensitive sensor, it's the one where upon small parametric variation, there is a large signal deviation. Then I can jump on that change in signal and figure out what's happening underneath. That quantity is the curvature of the Kullback-Leibler divergence, right? And the geometric intuition here is the following. Just 1 second, yeah. I have the space of probability distributions. This is X, and this is some probability distribution of X parameterized by the unknown parameter phi. But what I want to ask is not the question in this space. I want to move it over, and I want to think of a space of the parameter itself. So maybe phi 1 goes like this, phi 2 goes like this, right? And I want to ask if I'm at one point, that is the local tracking problem. If I'm at a given point here, given that my value of phi 1 is this value and my value of phi 2 is this value assigned by this point, the underlying probability distribution is that value, that histogram. Now I'm asking, what happens if I change, if I travel in any given direction? I did it for one parameter, right? So I only have one direction. So when I travel in one direction, what I'm asking is, what's the curvature in the space of probability distributions, right? And that curvature is the Fisher information, right? So right? It's not equal to, it's typically up to a constant, depending on how you define the distance measure. Yeah, there was a question. Oh yeah, sorry, yes. So it picks up a -1 there, the first one goes to 0, and there's a minus there, which gets rid of the whole thing, yeah. Right, so, and now that's correct. Yeah, thanks for that, yeah. Okay, yeah. Yes. Because it's local tracking. Your variation in the beam splitter's transmission coefficient is 1 part in 10 to the 5. With all good measure, you can forget about second order corrections. Yeah. Okay. Other questions? Good. Okay. So I believe I have one more derivation that I've hinted at. Oh yes, there's one more piece of information. So this is something tomorrow Saikat will take up more aggressively, but I just want to say this to you because this is also experimentally relevant. I could ask this question. I can say, look, I have a probability distribution that is parameterized by a parameter phi, and the distribution is over some variable x. And this variable I have measured in the lab. and I have frequencies. They're sitting in my computer right now. What do I do? Is everything that you just said, does any of this apply to me? Right? What do you do? What you do is plug it in here. This is the expectation, and you got some frequencies. So let me call those frequencies basically right? I'll ignore this difference between, I'll just assume that it's an experimentally derived probability distribution, right? Now, what am I to do? This is a fixed object. I can't touch this, right? So what I can do is I can write it out. It's sum over, or sum or integral, right? My curly phi's and straight phi's are the same. Yeah? Nothing. I've just repeated the, right? Now what do? I need the parameter phi. I made 500 measurements. I took 1,000,000 data points, right? So the 1,000,000 data points is the total sum over all the number of data points over all the different histogram indices that I've taken of the frequencies that I've registered, right? That's 1,000,000. And now I need to do something with it practically, right? In practical terms, I want to do something with it. I want to have some estimate of what my parameter is, right? It's a fair question, right? It's not 8 measurements like our typical simple pendulum high school experiments, right? It's 1,000,000. It's a fair number. You can ask, please tell me, right? So let's try and apply what we have learned. What can I touch, and what is the thing that I cannot touch? The experimental data new. I can't touch it. It's done, right? So what I can touch is basically the probability distribution P. So what I can ask is, I can ask for the phi that minimizes, right? Basically, sorry, I should have inverted these. My apologies, because that's the quantity I'm varying. My bad. Right? I should have inverted this because this is what I have and this is what I expect. And this expectation is what I'm trying to figure out. What is the best thing to expect? Right? I was like, what did I do? Yeah. Okay. So if I do this, I want the phi that minimizes S of nu given P. Right? So minimized over the probability distribution P of X given phi. So I vary the phi, right? Till I find the value of phi that minimizes this probability distribution. So let me just write it out. It's sum over nu I log nu I, or I can write it as integral nu of x comma phi log nu of x comma phi, right? Minus sum over nu I log pi, right? Which is the same as minus integral right? And now the first term, does it depend on the probability that I want to try and minimize over? No, right? It's just it's the data. It's simply the negative of the entropy of the data. Right? If you look in yesterday's notes, right? It's the minus sign of the entropy of the total data that I've collected, right? So it's some measure of the information content of the data. This quantity, on the other hand, I put a minus sign here. So this is the same thing. So let me call it let me say that this is the same thing as minimizing. So let me write in a different color. Same as maximizing basically over the probability distribution x comma phi, and the only fixed parameter here, the only variable parameter here is phi. Nu x comma phi log p of x comma phi, right? And nu is just a data set, so I'll just call it nu x, and integral dx nu x, right? So if I maximize this quantity, it's the same as minimizing the Kullback-Leibler divergence. Agreed? Right? This thing, this technique is actually something that you use in an experiment all day long. This is called max likelihood. Right? So it's called MLE, estimation. Right? And I will move on because I have to get to the quantum stuff, but Saikat will discuss this, right? So this is related to Bayesian estimators and so on and so forth, all of which is the story for tomorrow. Okay, before I end the classical lecture, I just want to say one last thing, which I will note over here. I apologize for my board work. I have a set of parameters here which are different from what I'm writing on the board. I'm constantly translating, which is causing some issues. So I want to just say two things to you, which then you can study later on. One is, they're both related to this thing, relationship of Fisher information to so there are two names here, Hellinger distance and Bhattacharya coefficient. And they're both basically related to formal distance measures in the space of probabilities. So you can just basically stop doing quantum mechanics for a month and go open a book on probability theory. And you can say, can I define distances between probability distributions? The answer is yes, there are many, many. And Ingmar Bengtsson and Karol Duchkowski's book on geometry of quantum states is an excellent place for us to study this, because the rest of the language, it's all integrated into one unified language. But I just want to state to you that there is this notion of Hellinger distance between two probabilities, p theta and p theta plus d theta, right? And this is 1 minus this Bhattacharya coefficient between p theta and p theta plus d theta. And this Bhattacharya coefficient is basically defined as the sum over the square root of basically p theta I and p theta plus d theta I, basically. So this thing called the Bhattacharya coefficient. And the crucial thing that I just want to make, which is the only thing I will say about this, is you can work out with a little bit of work that the Hellinger distance, as I defined between theta and theta plus d theta, sorry, phi and phi plus d phi, the Hellinger distance between these two quantities is exactly equal to the Fisher information divided by 8 times d theta squared plus higher order terms, right? So if you do it another way with Hellinger distance this time, then you get to the same answer, that the proportionality is the Fisher information. It's just that the number up front changes. Okay. So I just want to end by saying that you can make the following interpretation, which is Fisher this quantity that we've been calculating all day is the speed of probability distribution functions evolution, but it's the speed of Hellinger if you want to put it in some context, right? So think of the square root of Fisher as defining a speed. Yeah. Okay, good. So that is what I actually wanted to finish yesterday. So let me now quickly move on to quantum because I see I have 45 minutes. Yes. 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 It's some cousin of this. It's so the question that So the question that he's asking, I'll just repeat for the mic, which is if instead of having one data and one theory with an unknown parameter, if I have one data and two different theories, right, a Poisson distribution and a Gaussian distribution, what do I do with it, right? Is this problem relevant to you? It's actually very relevant to you because so there are several folks I met who are doing EIT, right? How do you tell Otler towns from EIT? It's a huge mess. If you look at the distribution, you can't tell, right? So there is a cousin of this called the IUCAA information criterion that you have to apply. It exactly the same mathematical principles underneath, but it's just something which penalizes you for adding more parameters, and then you can differentiate between different theories. Yeah, so I just say this, but I can point out the reference to you. The specific example that I just quoted of EIT versus Otler towns was worked out by folks in the group that I was in. So it's Barry Sanders in Calgary, and then John Dowling and Peter Anisimov, who John was my advisor. And so there's a PRL, you can look it up. Okay, good. So let me be very quick about this. What's the question in the quantum context again? I wanted to start the quantum context with what the general problem was. Right, and the general problem, let me just highlight with a diagram or a series of diagrams, which is, what do I do in standard metrology? I have a quantum state, psi naught that I send in. I have a unitary transformation U that acquires a phase phi. This is e to the I phi g that I've been writing, minus I phi g. And then I want to perform some sort of measurements, right? That I do by defining an estimator and trying to do it that way. Now, of course, the question I can ask is, I have quantum systems. And so unlike classical systems, I know that quantum systems can be entangled, right? They can be correlated. And in fact, the famous example, the one that Carl talked about for the last 2 days, of the equal superposition between the highest and lowest eigenvalue states, right? So this is a variety of entangled states. If there are many bodies underneath, if there are many qubits underneath. So you can ask the general question, let me just express the general anxiety that has been in the field for 20 years now. Well, much of this is resolved. So this is just the history of the question is, I can repeat this box of measurements n times, right? I'm putting tensor product because it's like I'm doing them in parallel. Mathematically, that's the structure. Or I could do something else. I could do several of these. I could do some big unitary U, which is an entangling unitary, And so for instance, it takes some fixed quantum state. I'll explain what fixed means in a second. And puts out a quantum state, which is this lambda plus small lambda divided by square root 2 that Carl alluded to, right? And he actually drew the diagram that does this as well for some cases. And then you could acquire phase individually, and then maybe you do something else. So sometimes this is called a kickback, a phase kickback. And then maybe you do some measurements. So there may be some strategy like this. And there are examples that you've seen, I'm sure, in Carl's talk today and yesterday. And so you could ask, is this a better strategy? Right? Well, clearly, this seems like a better strategy, right? And you could ask this question. And if the only question that we were answering was pure states and individual Hamiltonians, and you could do whatever measurements you wanted, then the story is done. The answer is exactly what was said to you, right? But what is the community, what the literature in the community is related to the fact that there is decoherence, for instance. And now you can't just look at such a strategy, because that strategy, as Carl said, deteriorates immediately and goes to square root n, right? So let me highlight again. So these kinds of strategies have a Fisher information. Now I'll refer to them as quantum Fisher information, which goes as square root n, which is the standard quantum limit. And these kind of strategies have a Fisher information that goes as n, square root Fisher information, right? Which goes as n, and this is basically what is called the Heisenberg limit, right? But I put this in quotes because you have to understand what that phrase means. It's adjacent to the uncertainty principle, but there are some caveats. We can talk about it offline. Anil is talking about nonlinear Hamiltonians. So let me just say what the point is. If you have nonlinear Hamiltonians, you can break this, and you're not breaking any uncertainty principles. It's simply the fact that all that this tells you is that if you have linear queries, then the best you can do with the Fisher information is go quadratically. So Fisher goes as n, square root Fisher goes as n, right? That's as well as you can do. So anyway, so having said that, here is a strategy which clearly produces less Fisher information than this. So in principle, the job's done, except for the fact that often we don't have pure states, often we don't have any entanglement that we wish to have, often that entanglement is not stable, often there is decoherence, often we don't have the measurements we want. And so optimizing over each of these little pieces has basically been the literature of the community for the last 20 odd years, yeah? And so I want you to understand that that's fundamentally one of the things that we've been dealing with. The second thing is that Fisher also, from this deep probability theory point of view, we found that it's very meaningful in all kinds of other places. So I want to actually end today's lecture by pointing out, hopefully pointing out to you, its use in a completely different area of physics than sensing, precision sensing, and then I'll loop it back around into precision sensing. Okay, so how do you spend your resources? This is the question. And there is another question which also you can ask, which deepens the problem further. This is all for what? Local tracking. If I know that the parameter exists between 0 and 2 pi and I need to find it, how do I do this, right? If you ask an experimentalist, those of you who are experimentalists, I have some oscillatory curve and I need you to find where I am on this curve. What will you do? You'll first take readings to try and locate, am I on this curve, am I on this curve, or am I on this curve? So let's say you're on the middle one. You spend some resources getting here, roughly. And then you sharpen the measurements and you get to that point. And you declare to me that that's where I think I am, using an estimator, right? So these are called 2-point strategies, or 2-stage strategies. So the first stage localizes you from the global to the local. And then the second stage refines the measurement and gets you where you want to go. What is the resource count for that? This is another question I can ask, right? And it turns out that those resource counts are typically no better than the standard quantum, even if you have entangling light in the background. So if you have entangled light in the background, but you don't know where you are between 0 and 2 pi, you're going to spend a huge amount of resources getting to the box where you could do this. You could ask, for those of you who are optics motivated. You could say, hey, maybe I do multiple reflections. Maybe I do something like a Fabry-Perot or something, where I do multiple passes and then I measure at the end. Does that produce something interesting? It does, but you have to work it out, right? And so all these kinds of queries about resource constraints, about decoherence and open quantum systems, and about basically local versus global strategies, this has been basically the story of the community, the questions that people have been asking, right? And right now, where we are is multi-parameter estimation. So multi-parameter estimation. And it's also trying to find good estimators that are experimentally viable and that can stand up to basically practical situations that people are interested in. Yeah, so that's a broad sweeping statement. Okay, so with this, what I want to do is go back to quantum mechanics. So I was faced this way when this question was asked tomorrow morning. So how many of you know what a POVM is? Okay, so this is good. So I'm going to be super brief about it because again, this is, but ask me at tea time and we can make a discussion. But so let me tell you as if we were running at high speeds. So within the context of quantum mechanics, right, what I want to do is introduce to you P of x comma phi within the context of quantum mechanics. So let me take a quantum state. I write it as Ci times I in some basis. What is the probability for measuring the state I? Mod Ci square, right? So the probability of measuring the state I is mod Ci square, right? And so this, another way of encoding this is to write I psi mod square, right? Just quantum mechanics 101. So more generally, so this is a probability already, right? So you can see probability distribution functions coming up. More generally, what you want to do is you want to relate basically quantum states which are in Hilbert space and some operators which exist in some space. You want to relate these quantities to some probability distribution functions, which you can then associate with numbers in a lab, with histograms in a lab, right? So this mathematical map is Bond's rule, right? The thing I just told you is Bond's rule, right? So what you want is basically, in the most general context, you want to put down the relationship between a measurement that I want to make, an operator which defines the measurement, the quantum state that I want to make this measurement over, and the probability, right? And so, okay, so what we can do is, we can ask what do these things, what properties do these things have? And let's construct the most mathematically convenient object. So the probability distribution functions have to have two properties. Property number one is that probability distribution functions, discrete or continuous, have to be positive semi-definite. And the second is that they have to sum to one, right? The total probability has to be one, and it has to be a positive semi-definite number, right? This is what probability distribution functions. So what I need is something that now I can put into more mathematical terms, which is I need something which is some function of my quantum state and some operator m, right? Let me call it m because I've called it m throughout, such that it maps onto this kind of object. And I just need to find what that object is, right? So we already have one in principle. And what is that object? We already have the operator p. So we already have the operator p, which I'll call pi, which are basically ii. And what property does pi have? Right? So pi has the following property that if I choose a pure state I, Then for any pure state I, this outer product Pi has the property that the expectation value in a quantum state is a positive semi-definite number, which we associate from Bond's rule as the probability of seeing that outcome. And the second thing is that from the completeness, if Pi, a set of Pi's are chosen such that they form a basis, the underlying states form a basis, then from completeness, basically, I can write sum over I to be equal to the identity operator, and then I can just complete that, and that's just the number one, right? So a full set of projectors, as it's called, basically, is a good candidate for a measurement because it produces a probability distribution Pi, and now I know how to deal with this, right? So this is one set, right? But this is not all of it. And the reason why this is not all of it is basically because there are several properties of Pi that we don't need, that come extra here. So the properties of Pi, let me just draw them here. Right? Sum over Pi is identity. Pi are positive semi-definite operators, which means that any expectation value in states basically gives you the same, right? And then Pi square is Pi. And this is the crucial third object which you don't need. You can actually get rid of it completely. And it's just a mathematical convenience and just the way from Bond's rule and typical quantum mechanics that we would arrive at this, right? Okay, so if you got rid of it, what do you get? What you get, okay, so before I get to that, sorry, I just have to say one more thing, which is, what does the post-measurement state look like? Right? I apply the projection operator Pi on the quantum state psi, and then what do I get? I get I on psi, right? But that's not that's an unnormalized vector, right? Actually, what I have to do is divide by psi Pi psi to the half. And so this is the square root of the probability. And if I divide by the square root of the probability of the outcome I, then what I get is just the outcome I up to a global phase, basically. Yeah. So this basically is the full representation of a projective measurement, including the post-measurement state. And all the probabilities are encoded and all the, so when you measure a state and you say that I have gotten the outcome I, my quantum state is in state I, this is what you mean mathematically. Okay. So let me pause and take a sip while addressing any quick questions. All clear? She's shaking her head saying no. So tell me what is not clear. Just say. What projectors mean, right? Good. Exactly what I want to hear, right? So let me give you a very simple optics example, which perhaps clears it up, right? So what I have is some quantity, I will refer to it as a wave function, but if you want to think of it as an electric field or something, which basically exists all over some space, right? Now, what you want to do is you want to ask how much of this light is available in a given place. What would you do? What you would do is actually put a mask, right? And by this, what I'm doing is I'm just allowing a little bit of light in, right? I put a mask down only in this place, and then you put a detector under it, right? Then if it's a photo detector, which can detect the incoming incident radiation, right, intensity of the radiation, then you have an accurate measure of what I've just drawn as a cartoon, right? Now, what is the problem here? The problem here is that if I just take that little width, that window that I've drawn, and I shrink it all the way to 0, you're measuring everywhere on the real line. That is a projective measurement, right? Because what you're asking in the context of a 2-level atom is you're saying, or a 3-level atom is you're saying, my quantum state is in some superposition of these three. Is it here? What is it here? What is it experimentally? Typically, if you ask one of the NV centrist people who are sitting here, they'll pump it out to something and then that will decay, and you look at the fluorescence, right, that this thing produces, right? So what have you done? You've actually created some sort of mask on the other two, and you're just staring at this guy. Right? These two are the same, right? Classically. This classical electric field experiment that I've done. So that's a projective measurement. And the projective measurement projects you onto a quantum state which has no other uncertainty left in it. It's a pure state. So if you ask the question again, so once you have measured the quantum state and it registers as it was here, if you ask the question again, where do you find it? Here only, right? And that's the reason why P square is P. But you could ask a different question, and this motivates the next thing that I want to say, which is you could say, I don't want to make it very thin. I'll ask, is my quantum state in this box or in this box, right? So is it in the left half or the right half of the detector, right? Now what kind of question are you asking? You're asking a question that doesn't have fine details attached to it, right? But it has some broad information that is sitting here, right? So now if you ask the question again, you might get a different answer, right? And so this kind of measurement is not something, this is like asking, are you in this top 2/3 of the quantum states, or are you in the ground state, right? And if you get the answer, yes, you were over here, the next time you can get a different answer, right? So when you project multiple times, when you measure multiple times onto a selective measurement, which is so selective that it leaves no other choice, you get what's called a projective measurement. And a projective measurement is defined by this mathematical creature. And what it actually is saying in words is it's saying there is nothing left in there except a pure state. So if you measure again and again, you get the same answer. Whereas if you have basically other outcomes, which I'll show you what I mean by this. I'm being vague for some reason. I haven't introduced density matrices. If you get basically more general answers, like asking, am I in the left half of the detector or the right half of the detector, repeating this measurement has not yet exhausted all of the information that's sitting there. You have not asked such a fine question that you can get no other answer. There are other options that are lingering around, right? In the half plane. And because of this, you can get basically multiple repeated measurements can change the quantum state. And that kind of an object is the more general measurement, which is what Carl was referring to today morning, a POVM, right? So the most general quantum measurement is the one where if you measure twice, you get your quantum state is actually two different things, right? It changes twice in general. A specific subset of that is where it doesn't change, right? The thing that changes upon repeated measurements is the more general object. And then a subset of it is a thing that doesn't change at all, right? So this is clear to everyone, right? So projective measurements are a subset, are a special class of POVMs, right? And I'll introduce POVMs in a second. Go ahead.
Because
we
in experiment we have a burden of using Ansel at the moment we go to POVM, right?
In general, not necessarily the case. Let me just say. So let me just very quickly repeat the question. He's saying, look, in an experiment, POVMs have to include an Ansel. Why he's saying this, I will explain to you offline. So isn't it more difficult to do POVMs? Why, right? So let me just restate what the job is, right? The job for the last 2-3 days of this conference, right, is basically to establish mathematical bounds and show you the experimental reality, right? And so when you're doing mathematical bounds, you have to allow the most general mathematical theory that is allowed. And so I have to allow for a measurement setup where upon repeated measurement, I keep getting different answers. That is the most general setup that I have, right? What it actually means in principle, if you want a kind of a more experimental sounding answer, which is not really, is to go back to kind of these original formulations of what a measurement is. So the way in which we envision a measurement is that I have a quantum system, I correlate it to another system, and then I measure that system in a pure state, right? I project it onto a pure state. If you project it, if you correlate it in some particular way where you have a one-to-one relationship between the outcomes that you want and the measurements that you perform, then basically what you get is projective measurements. But in general, and this is in fact part of the current work that I'm doing if you go to the archive and look up my papers, you'll see some MLE, blah, 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 is to ask the question, what happens if I only have thermodynamic constraints, right? So projective measurements are zero temperature measurements. They're not thermodynamically consistent. So if I basically allow myself only thermal resources, what can I do? And then what happens is naturally you get stuck with POVMs. So the question of whether POVMs are natural or not, I want to just say that maybe there is more here, right? And I point, let me just give you one reference, give everyone one reference. So there is a paper by, I think it's Elena Guryaneva, Marcus Huber, and Fries, Nikolai Fries. I might be mispronouncing their names, I apologize. And they've written a very nice paper. It's cited in my paper, so you can look my name up and then find it through that. It's a very nice paper on thermodynamically consistent measurements. Yeah. So anyway, topic for another time. But let me just also say one other way of thinking. I want to give you multiple perspectives as I understand it. Think of a laser, some sort of measurement, not a laser, but some sort of optical measurement where you have a lens and then you have a detection plane on which you put a detector. If you don't focus the lens down to a point, which you can never, right? Point spread functions and all that, you can never focus it down to a point, then actually you're not collecting point information. And you're stuck with collecting over regions. Basically, when you try and project it back, where did that come from, right? So the more natural object, I will say, given experimental constraints and reality, is measurements of this form. Is it in the box? Is it outside the box? Right? It's an idealization for us to take the box down to zero. And it's an idealization for us to assume that that box doesn't care about temperature. That doesn't care about temperature works perfectly fine if you're in infinite dimensions. So for all of you who have some sort of harmonic oscillator modes, right, optics and so on and so on, ion traps, you're good. This doesn't apply to you.
Yeah, so another thing, what you were saying, I just thought that when a system interacts with a bath,
yes,
and you unravel the master equation, you get the cross operators, you view that as projective, POVMs only. So
yeah, you're using language I haven't introduced, but yes.
No, so I'm saying the bath also does POVM on the system. Can that be also thought as a POVM or more natural than projective measurement?
That's exactly what I just said. Yeah.
Okay.
So the moment you have thermodynamic resources at hand and you constrain yourself that way, then POVMs become more natural than projectors. But this is an advanced point. Yeah. So let me just we can discuss that offline. Yeah. Yes.
If we combine different projectors with
Yes.
classical probability, like that is a kind of POVM then. Like different projectors have different.
Oh yeah. Sure. Yes. You can think of basically, I collect information about am I in the ground state, the first excited state, or the second excited state? But then I'm foolish and I forget to write down which one was the first excited and which one was the second excited. Then I'm actually doing essentially, I'm collapsing that piece of information, and you go back to POVMs.
Is the thermodynamic description also similar to this kind? Like you?
No, sorry, I opened a Pandora's box, which I'm very interested in, but no. Let's just leave thermodynamics out of this just for a second. Yeah?
I have just one clarification. So you are normalizing there, right? So there won't be any sum over I.
No, this is just I have two detectors. One for horizontal polarization, one for vertical polarization. My vertical polarizer went click. Now, what is the quantum state, right? And you need to normalize by the probability of seeing, the square root of the probability of seeing that state so that you get a normalized state out the other. Yeah. Okay, thanks a lot. Yeah. Good. I have 16 minutes, which is, I feel like Keanu Reeves in the movie Speed and Speed 2. So maybe I finish POVMs and then I'll have to continue on. So you can write a more general object, right? So essentially, what do we want? This we absolutely want because this is probability conservation. This we absolutely want because that is probabilities. I want it to be a probability that I measure in the lab. It has to be a conserved quantity because all the probabilities have to add to 1. I don't need this. That's extra. So let's get rid of it and ask the following question. What kind of matrices or what kind of operators exist which basically satisfy the first two properties alone. And then you get POVMs. So just for brevity and to be the Keanu of this lecture, let me define these objects. Right? If I write a matrix, I'm writing script E because I have estimators or this boldface E's. These curly mathcal E's. If I have an operator, a matrix like this, you just have to take it from me. I mean, this is a linear algebra thing. You can look it up on, like, in Artin's book or whatever. These quantities are called basically positive operators. And what that means is that for any vector that you take, is positive semi-definite, right? And you can see why, because if I just insert the format that I've written, it looks like some vector and then the Hermitian conjugate of that vector. So it's clearly basically just the inner product of the vector with itself, which is real, right? So that's the reason why. So these quantities are the most general objects. And what property do you want them to have? The property you want them to have is that sum over, so what is the probability pk that I assign to it? It's trace, sorry, let me write it for pure states first. Psi epsilon k on psi, right? So the probability pk associated with this now more general measurement outcome ek is basically the expectation value in the state psi. Yeah? I've done nothing. I've just exactly done the same thing as I did before. It's blatantly positive semi-definite, right? So I can assign it to a probability. I can say that it is a probability, right? Good. Good, okay. So what do I want probabilities to? I want probabilities to do is to add to 1, right? But let's actually sum over k, psi, ek, psi. And I can pull the sum over k, ek in here. And this is psi, sum over k, ek, psi. And like before, I haven't told you what psi is. Psi is any arbitrary vector, right, in the Hilbert space, which means that this quantity is basically forced to be equal to the identity operator. So that gives us the condition, which is epsilon k summed over k must be the identity, or to write it in form of the matrices that make this positivity self-evident, it has to be this. Yeah. So these quantities are called, and now epsilon k squared has no need to be epsilon k. I'll give you an explicit example before we leave. But this set of things define what is called a I'll explain why this is called this. So it's called POVM. Some books will call this POM, positive operator measures. And I can, some small difference which we don't have to argue about right now. And these operators are called Krauss operators or Sudarshan Krauss operators. Right? And this form is related to something called an operator sum representation, which I'll tell you about at some point. Okay. So just to prove the point that these objects exist, and I just didn't write a bunch of random maths, I wanted to leave you with an example. And this is another of my homeworks, for today, is consider 3 quantum states. right? Prove that PA, P plus, P minus are a POVM, where PA is AA and P plus minus is plus minus, right? B plus minus. Right? Prove that this is actually a PAVM. No. Yeah. And it goes, if you want to think of it quantum mechanically, it goes to that question he's asking about probabilities. Right? Okay. Okay. So I have 9 minutes, and let me just say what is on hand, which I have not done. So I wanted to derive today the Kramer-Rao bound, which the quantum Kramer-Rao bound, including the derivative of the bias. Can I ask the organizer, can I just go like 15 more minutes? Okay, so that's perfectly fine. Is everyone okay? Do you want to take a break? Because I already have 10 minutes. I'm bargaining for more time. Yes, extra time. So can I go 15, 20 minutes more and then we stop? I'll tell you the reason why, because I spoke briefly to Saikat Guha about his lecture, because he's introducing a bunch of estimation theory as well. And we were trying to sync up our lectures. And I promised that I will do quantum Kramer-Rao bound, which I have not gotten to. So let me just do that, and then I stop. Yeah, so that I'm consistent at least to the promise. I'll try to keep the promise, so that he can deliver his lecture without altering it. Okay, good. So there is just one more piece of kind of basic quantum mechanics that I have to do, and then off I go. And the reason why I wanted to do both of these is one, because Carl brought it up today, but also because my understanding is that his lecture next week is about the general theory of Krauss operators and POVMs, which you should understand. So, this is my hope to kind of get you somewhere. Okay. So the last piece of basic physics that I want to introduce to you is density matrices. And then we throw both of these into a box and run away to UCRB, quantum Kramer-Rao bounds. So this is the last piece of the puzzle that I want to, I've written nothing down. I just said introduce density matrices. So I'm going to riff, and you can tell me if this works. So how do you discuss the physics of, let's say, two atoms next to each other? One of these, I would write a quantum state psi. How would I write two of these? Tensor product, right? Does everyone know this? Okay, very good. Right? So what I want to do is ask the question, how do I discuss the physics of a damped harmonic oscillator in the quantum universe, right? Or more generally, I have some physical system here, and it's part of an environment over here, and the system and the environment are talking to each other. What's the description of just my system? How do I think about this? Right? Another way of asking this question is that there are just ancillar degrees of freedom that are lying around that I don't want to measure. Right? Maybe they're not endowed with all of the nuisance properties of environments. They're not thermal or whatever, but I don't care about them. So if I want to think about subsystems of systems, what's the consistent description? Do I have to write the physics of the entire universe, right? Is this a question that you've handled before? Yeah, how many of you? Right? How many of you know density matrices? Because if you do, then I can just skip. Okay, perfect. Almost all of you? There are some people. How many of you don't know? Sorry, I just need hands so that I can skip over this. Okay, so there's one person, which means I'm just going to basically cut short the discussion very quickly, and I'll talk to you offline, yeah, if it's all the same. So the short discussion is the following, which is I can write a quantum state in the system environment space using, in some basis, I can write it as basically sum over I and j, Cij times some matrix psi I, tensor some matrix phi j, and this is in the system and this is in the environment, right? Now, what I can do is I can basically diagonalize this matrix using singular value decomposition, and I can write it as sum over alpha times lambda alpha times u alpha tensor v alpha. And the promise that I have is that lambda alphas are basically like the square roots of probabilities. So if you square them, they have, the positive semi-definite in the squares of them add to 1. And u beta is delta alpha beta. And so these spaces continue to retain their orthonormality. Right? And if you don't know how to go from this step to this step, it's 3 lines of algebra. I'll show you offline. Yeah. This you agree is a general quantum state in a tensor product space. That's simply some cousin of it, which is diagonalized very nicely. Okay. But what does this allow me to do? It allows me to ask the following question. I can say, I want to know only some expectation value of some system operator AS. And what is this quantity? I can calculate it's alpha prime, or more before that, it is psi SE, a tensor identity, psi SE, which is sum over alpha and alpha prime, or alpha and beta. Basically, lambda alpha, lambda beta times u alpha a u beta, v alpha v beta. But this quantity is delta alpha beta. And so what you get is sum over alpha, lambda alpha squared, which I just called T alpha, times u alpha a u alpha. And so what I can do is I can compactly write this as the trace of some object rho times some object A, where rho is now identified as sum over alpha, P alpha, U alpha, which is the spectral decomposition of the density matrix. And it simply asserts the fact that there exist these objects, which are called density matrices. They are positive semi-definite matrices. So rho is rho dagger, rho is positive semi-definite, trace rho is 1. So these are the properties of a density matrix, right? And if trace rho squared is 1, this is only for pure states, right? And it essentially says to you that, well, you don't care about the other subsystem, and so you lose this information. And so what you're doing is probabilistically mixing with probability P alpha, the quantum states U alpha, whose expectation value you seek, right? So density matrices encode this probabilistic information and simultaneously become a larger set of the system states. So pure states become a subset of them, and are simultaneously also derived from pure states of an even larger object, right? Okay, good. So that's succinctly what density matrices are. And with all of this introduction, I can basically just show you QCRB and we can get out of here. Okay. So with all of this, I want to ask the following question, which is, so this is a famous derivation. It's by Hellstrom. And so it starts with our friend B of phi. So the bias, right? And what is this bias? The bias is the trace of rho phi times m minus phi, right? So let me explain what I've just written to you. Trace of the density matrix is 1, which means that that object is just phi. So this is trace of m rho phi minus phi. But this trace of m rho phi is basically our estimator phi, right? So this is what Carl was also writing in the morning, which is I have some measurement and I can get rid of all of the kind of systematic bias from it. And then I can write it in such a way that literally just the expectation value of it is the estimator that I'm looking for, right? Now you actually have to do this because you have to go through the classical estimation literature, construct this unbiased estimator, blah, 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 and do, work out this. Some measurement operator. I'll give you examples. It's a part of in general, a POVM, which is the reason I introduced it, right? So it is some general measurement, but it's one of the measured quantities. So let me give you an example. Suppose you basically measure spin up and spin down, Stern-Gerlach kind of setup. You can ask that the difference between the number of up versus down be the thing that you use to estimate, right? And when you use that difference as the number, basically, that's that quantity n1 minus n2 or sigma z expectation value, whether it's bosonic or fermionic, right? Is that quantity. So you are measuring just intensity difference between the two arms, right? The intensity, the sum of the intensity is a conserved quantity in that case, right? So there is you're doing something where there is a complete measurement sitting around, but you're doing typically you're just measuring one piece of it or a few pieces of it, yeah? Okay. So this is the bias, right? So all that I'm going to do is just manipulate it for about 5 minutes and we'll all drink tea. So take a derivative with respect to and what is this quantity? It has two terms. Oh, sorry, one thing that I want to say is that rho phi you can think of as u phi rho naught u phi dagger. So u phi is e to the minus I phi times d if you want, right? There's a more general context that you can put down, but everything I'm saying doesn't depend on this. But if you're uncomfortable with, hey, what is this density matrix with something under it that you have written? It's that density matrix that has been evolved by an unknown parameter. Why density matrix? Because I couldn't control it well enough. I wanted all spin up. I got a little bit of spin down. Yeah, that's the sense in which I want to say this. Okay, there are two terms here. That depends on it. So let me put a del phi rho phi and then m minus phi. And then that has it as well, but that's just a minus 1. Yeah. So now I can collect and I can write 1 plus del phi b of phi squared is trace of del phi rho phi times m minus phi squared. Right? So now you have a little bit of a technical problem. So we did this in classical estimation as well. And when we did this in classical estimation, there were no matrices around. There were no fundamental matrices around. Even for a single parameter estimation, there were no matrices around. There were just functions. So when you took objects like this, there's no problem. There's no fundamental problem with all of this, right? I'm going towards a variance, right? So with that hindsight, let me just point out to you that this right-hand side quantity doesn't look good. Why does it not look good? Because that quantity is a one-sided derivative. right? And so it doesn't have a symmetric, role. It doesn't come in a symmetric form here. And because it doesn't come in a symmetric form, in general, this quantity is complex if you just try and do it. This was the question that I had asked Carl in the morning, right? So if you try and handle this by just doing a one-sided derivative, whatever that sentence means, then you run into basically the problem that you have more errors. So I want to go to the lowest error. So with the hindsight of Hellstrom and then Brownstein and Caves, so on and so forth. Why? No, first I'm just taking this derivative. Ye chhod diya maine. I left this alone. Then I left this alone. I took the derivative of this. So I just get minus 5 times the trace of rho, which is 1. Minus d5 by d5 times trace of rho. Yeah. So that minus 1 is correct. I'll just tell you why offline. Yeah. So what I do is I propose now to fix this problem. I propose del phi of rho phi is equal to some quantity. I don't know what this quantity is. L phi rho phi plus rho phi L phi divided by 2. And this quantity is the symmetric logarithmic derivative, right? And the motivation for it should be clear to you, right? This is an absurd sounding equation. I'm confused by this even today, right? But the motivation is clear to you. If I am allowed to replace this quantity with that quantity, then I can write whatever is in that bracket squared is a real quantity, because then I have basically some antisymmetric quantity, right? Times some. Okay. So now, how do you solve this? It's a tricky business, right? Let me hint at it, because this is a complicated derivation. It's a long derivation that you have to do. So what you do is you write rho phi, right, which is this parametrized density matrix, as basically sum over P of phi of k, right, times UK of phi, UK of phi, right? Let me actually just look at what notation I've used, because I don't want to start inventing notation. Yes, of course. So I choose to write my density matrix as this quantity, which excuse me that these are probabilities now. These are probabilities, PDFs, and lambda k, otherwise I'll be here not reproducing any of the formulas correctly. And then what you have to do is you take the derivative of phi. And what you get is you get a term which is basically like derivative of phi of lambda k of phi. And then you just get the eigenvectors, plus you get a lambda k times the derivative of lambda k of phi, right, plus Hermitian conjugate. And now what you do is basically you set this equal to an abstract vector, an abstract matrix of the form L phi rho phi plus rho phi L phi divided by 2. And then what you do is you write rho phi again as sum over k prime lambda k prime of phi lambda k prime lambda k prime, and you insert the whole thing and you stare at it long enough and you can invert this. Okay, so this is how you would construct the symmetric logarithmic derivative. It's a little bit of algebra, but I've essentially told you what the trick is to do it. Okay, so with this, let me just continue on. So what I have is 1 plus del phi of d phi squared is equal to the trace of L phi rho phi plus rho phi L phi by 2 times this measurement minus phi. Right? You can convince yourself by just expanding the first term and the second term and then flipping it around with cyclic trace, that this is equal to the real part of the trace of m minus phi times L phi rho squared. But this is less than or equal to, and this is one of the less than or equal to's that Carl mentioned today. The trace, the absolute value of the trace of m minus phi times L phi rho mod squared, and this with some blah 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 is less than or equal to the trace of L phi squared rho and the trace of m minus phi squared rho. And that brings us to the Kramer-Rao bound, which is the mean squared error of the estimator phi, which is that quantity right there, is basically larger than or equal to 1 plus del phi rho phi squared divided by trace of L square phi rho. Okay, and again, because L, you can set the expectation value to 0, you can identify that bottom line, the thing on the bottom, with the quantum Fisher information. And this is the quantum Kramer-Rao bound. Okay, so I'll stop for today. Any questions?
Like those who have questions can stay and interact with him if you are free, or if you want to have offline discussion outside.
Yeah, sounds good.
Otherwise, other people are free to go out. Okay.
Okay, thank you, everyone. Thank you.